Hi, today I have prepared for you a video about tension members. These are mostly diagonals. They cannot accept pressure, negative axial force, and they're used mainly for diagonals in steel structures. My name is Ivan Beleš and I am support engineer for Idea Statica and Scia engineer. Now we are in Scia engineer and I have prepared a very simple small structure with 4 diagonals, and we go through 4 chapters. One is the input, then the analysis with the settings of the solver, for example, then the results, and what you have to do in the steel checks. So first, if you want to, this is a nonlinear calculation, but not geometrical nonlinear calculation like theory second order, but this is physically nonlinear calculation. That means the members, if they get pressure, the calculation is iterative, and if the members get pressure, they will be deactivated from the structure, removed from the structure. This removing is done in blocks, and sometimes they can get back tension force and they can be also activated. This is for some special structures like some spheres or something else. So what we have to do is to activate this nonlinearity. You can do it in the project settings. You go to functionality and there is nonlinearity, and in the nonlinearity we use this beam local nonlinearity. This is everything what we need. Climatic loads are activated because I have already defined wind load with this 3D wind load engine. If we have the functionality activated, then we have to put this nonlinearity to the members. But there is also another different property of the member, and this is this FEM type. So we can change it to axial force only. So these beams will now get only axial force. I don't need to define hinges on the end of these beams, because also if you define local load, this load will be recalculated to the nodal nodes, and this beam is not loaded locally. It has only pressure and tension force at the moment, both forces. This axial force only is not a nonlinearity. This is only a definition of the which forces can this member accept. The one effect of these axial force only members is that they have only one finite element, because they have no bending stiffness. And if we would split these members to, for example, 5 or 10 finite elements without the bending stiffness, they would be collapse also for small pressure force. So that means they have only one finite element. This is an advantage, for example, for the stability analysis, because they don't get local buckling shapes. So we have defined this local axial force only members. If you don't like these big circles, then you can go to scale settings and down to these symbols, and this is the line symbols. For example, 0.1 is a little bit better. Now we can add the nonlinearity. The nonlinearity you can find in the, if we go to the structure, for example, then it's less. We can also limit to 1D members. No, to what is the boundary condition? Press tracing, load panels, model. I think boundary conditions, yes. Nonlinearity 1D, and that's very simple. We select tension only. Okay, and then select the members, or you can select the members before you start this action. So this is the first part. So we have defined the structure, and we need to calculate nonlinear, that means we have to explode the standard Eurocode combinations to linear combinations and read them to the nonlinear combination. And then for each nonlinear combination, one structure will be calculated. Because in the nonlinear calculation, the principle of the superposition is not valid, so we have to create first the nonlinear combinations with all loads, with safety factors, and then perform iterative the analysis. So we can go to the combinations. They are already here. They are defined automatically. I change it. First, I did it in German. Ultimate limit state, for example, 6.10. This is the formula in Eurocode. It's defined. So if you want to check it, then you can. Oh, sorry. You can go to the combinations and you can simply look at the content of the combination, and then you see the safety factors. So you see the winds. This is envelope. That means this envelope will be in the background exploded to a lot of linear combinations with only one wind. So this is only that you can check the safety factors. And now we can create so we didn't explode it. Yes, this was only to look at it with this content of combination. So you don't need to explode to envelopes or explode to linear. First, we need a calculation, a linear calculation. Only linear. Why? Because in the linear calculations, the engineer can calculate the critical combinations which are responsible for the maximum of reactions, internal forces, and stresses, and we can then say we want to read to the nonlinear combinations only these critical linear combinations, not everything, because sometimes you get billions of combinations. So we go to the nonlinear combinations, and because there is no one combinations, the engineer asks to create a new one. So I don't want to do it manually. I use this generator, new from linear, from combinations, and I can select linear. So I don't have linear combinations in my model. I have only the Eurocode combination, and this is an envelope. So I can select this Eurocode, and what should the engineer do with it? So we can create for each possible combination of this Eurocode combination, for each possible linear combination from the Eurocode combination, one nonlinear combination. But sometimes this would explode to millions or billions. We can say all dangerous, then the engineer calculates which combination is critical for reactions, internal forces and stresses, and only this will be used. But if also this is too much, then you can go to most dangerous, and then you can say how much, or money, I don't know, combinations, nonlinear combination do you want to have. And then the principle is that the engineer looks for the combination, for example, 1. And combination 1 creates, for example, 20 extreme values on some members. Combination 2 creates 100 of them. So that means the combination 2 is more important because it creates more extreme values, and this will be the first one. The second one is, for example, the combination 1, and if you have some other combinations, then they will be also used. That means the importance of the combination with this limitation of this on these numbers is how much extreme values on the members creates this combination. So I will say, because it's a small example, I say all dangerous, okay, and then I see I have 10 combinations. That's okay, and these are nonlinear combinations. Now we can run the we don't go to the nonlinear calculation. First, I look at the solver settings. Calculation mesh. Look at the mesh settings firstly. I have average number of 1D mesh elements on striked 1D member is 1. This is enough because we don't perform some dynamic calculation, stability calculation, or second order theory. This is still first order theory, only with this physical nonlinearity. So that means this is okay here. Then look at the solver settings. In the solver settings, you have this nonlinearity calculation. Sometimes maybe you have very large structure and the diagonals will be turned off one after the another, and for each for example floor you need one iteration, then this 20 will be not enough, so then you have to, then you get a message that the calculation was finished because of the maximum amount of the iterations, then you have to increase it. So you don't need to go to Newton-Raphson or something else. This is not second order calculation. It's only nonlinear calculation. So we don't need to change there something. And now we can run the calculation, linear and nonlinear too, and run the calculation. Now the calculation will be run 10 times because we have 10 nonlinear combinations. Okay, so we see for the linear calculation we have 3.5 millimeters, but this is only for some load case, and the nonlinear calculation is for the combinations, is for the combination number 3. So I can close it, and one explanation. Sometimes it will happen that after this calculation you will get a message about singularity. And for example, we have here these diagonals, and here are hinges. And this is a frame. This is also a frame without hinges. Then we have hinged supports. What happened if we load this structure only with vertical load? Then we get no horizontal forces and we get only pressure in these diagonals. And because we told Scia engineer to remove these 1D members which get pressure, negative axial force, then we will get such type of structure, a frame, second frame, and connect it with hinges, and the hinges also here. That means this will collapse in this or the another direction. So this will go down. What can you do with it? Sometimes I generate a very small horizontal force, for example 1 kilonewton. This is 100 kilograms, nothing. You can also define some inclination in these nonlinear combinations, but usually we have here the x and the y and the z axis. Then I create a small spring around the x and y axis with 0.00030 zeros or 4 zeros, 1 meganewton meter per radian. This is a very weak spring. So if it is loaded, then it goes down, but if it is not loaded, then it stabilizes my structure enough. So, but I didn't get this message now, so probably the solver team did something that it don't happen. Okay, this was about the analysis. We have the analysis finished, and we can check the results. The nonlinear results you can see only from nonlinear combinations or from result class, which consists of nonlinear combinations. So if we go to the results, axial forces, I select, for example, only these members. I do it manually. Maybe a little bit back. If you want to remove these symbols, then right mouse button, go to the view settings, and then in the model there is internal, there must be, now this is in the structure, member nonlinearities here, this. So you can deactivate it, for example, apply, it's out, or activate. And also these circles, these are these fem types, can be activated or deactivated. Okay, know the results. For example, from self-weight, it's German Eigengewicht. And then refresh, not for all, but for current, and I select these 4 members, refresh it. So you see I have pressure, very small, but there is pressure. This is for linear calculation. So the load cases are calculated linear. So if you want to see the nonlinear results, you have to go to nonlinear combinations, and we have these 10 combinations. Refresh, then we should get no axial, no pressure, because these members are excluded from the calculation. Not each time, because you can have some structure with these diagonals and you have very small force, or it's not loaded, for example. It's only self-weight. The self-weight goes through the columns and these diagonals are not loaded. And then what we get for results, we get some tension. In the middle there is no zero axial force, and on the bottom we have pressure. So we have axial force, we have tension, and we have pressure. In the middle the N is equal 0 kilonewton, for example. In this case, the engineer don't exclude this member because it's not a pressed member. We have told only the tension member should remain in the structure, but this is not tension, not pressure, it's nothing, so it remains in the structure. So this is one special case when you can get also very small negative axial force. So, but we cannot look 1000 nonlinear combinations. For this we have there are the result classes, and you can create a new result class. Is there some? Okay, I will delete this one, create a new one. New result class, nonlinear combinations. The name is result class NL ultimate limit state. You have to be careful. Don't include in this result class also some linear combinations, for example, from earthquake or some load cases, because this will damage your results. Then you see a mixture of linear and nonlinear results. This will not work. So therefore, if you want to look the nonlinear results, only nonlinear combination in one result class. And then we will see an envelope. So we can go to result classes, look at this one, refresh, and we see only tension forces. We can go to member results, and for each member we get only tension. If we have this case that the member was not excluded from the calculation because in the middle there is zero axial force, then you get on a part of this member also negative axial force, and the engineer will start the buckling check. So in this case, you can go to steel, where is steel? Here is steel, then to the, not to the settings. I go to all categories, and here I select steel. And I have this steel member data, and in steel member data I can say only section check. Okay, and then I can select the members. I had yesterday this question from a customer, and he asked me then, why can I simply not exclude the buckling check, and I don't need to perform this nonlinear analysis. But if you perform linear analysis, then you have a different structure, different reactions, different axial forces, if you compare it to the nonlinear calculation with the excluded tension members. So therefore, this is a combination only in the case you have this case that you get a small pressure on your member. And I think this is everything. We can look at the check, select this diagonal, so I can select everything, go to classes from the nonlinear combinations, extreme value from member, refresh everything, look at the results. Okay, they are not okay, this is my selection, but you see we have no issue with the diagonals, and the diagonals are very small member. This is only rod with 18 millimeters diameter. So I hope this is everything. So I can exclude this from the calculation and run the check again for this current. Okay, and you see also if we have the stability check, it's not necessary because we have only tension force. We can go to the global results, look at the detailed output tables and formulas, for example, and preview, and then we get the check, and we can check the check. so then we have section check, tension, and that's everything. So because there is no pressure force, there is not necessary to calculate some stability check. This is not okay. This is not important. So I hope it was clear for you, and thank you for watching. Bye.